So today we will talk about the connections. I would call them logical connections of field effect transistors. So metal oxide semiconductor field effect transistors, we can connect them in some special ways that will start to do some work for us as, programmers. So in something like 1960s, some scientists in Silicon Valley decided that they would like to try connecting field effect transistors in certain ways. One of which was the following. So I will draw here 5-volt supply. I use 5 volts as an example because in reality, modern microcontrollers and processors can work also down to 0.9 volts as well. It's just simple, more robust, more industrial processors use a bit higher voltage because of larger transistors. Okay, so generally, the transistors are connected in this way, where you have 2 field effect transistors in series, right, between power supply and ground. So does any one of you remember which field effect transistor we use in the top part and which one we use in the bottom part? You can write in the chat. So we have 2 options: N-channel field effect transistors and P-channel field effect transistors. So which one goes in the upper part and which one goes in the lower part of the circuit? You can write your answers in the chat. I see, somebody says P for upper part. Okay, and which one for the lower part? Okay, correct. So that is absolutely correct. Let's see. So the P channel field effect transistors go in the upper shoulder of this series circuit because we need to apply low voltage to open them, because low voltage attracts P carriers, and with low voltage the channel appears. So here we use P channel transistors, and in the bottom part N-channel transistors, because these ones we open with high voltage. With low voltage, they are switched off. If we swap them, both of them will never be open. And remember, the arrow goes from P to N. So if the channel is P, then arrow goes from P channel to N bulk. And if the channel is N, then the arrow goes from P bulk to, or P wafer to N channel, so like this. And I will write also with letters P and N, but these arrows are the ones that explain which transistor it is. So writing the letter was kind of just, for clarification. And so people decided that they want to connect transistors in this way. So they would connect P and N channel gates together and call this an input A. And the midpoint between these 2 transistors will be called output letter Q. So first of all, these transistors will be used only as switches. We will not use them as analog amplifiers or something like that. We will only work with signals that set the transistors either completely open, short circuit, or completely closed as not conducting or open circuit. So therefore, we will be talking only about logic levels. For example, A can only be high, meaning connected to power supply, or low, meaning connected to ground. A can only be 0, which means 0 volts, or logical 1, high, which means power supply, often called VCC, or also VDD, like from drain. Though both of these don't really have any meaning, it's just however people in datasheets tend to write them. VCC or VDD is power supply. In this case, it's, for example, 5 volts in our example. Okay, so I'll delete this one so you don't get confused. Let's say we're using something like 5-volt microcontroller, for example, Arduino. So now my question to you is, what happens? Well, first of all, how many levels of input do I have? You would agree that I can only have 2 levels of input, either high or low for A. So A can be either low or high. Now, please tell me, what is the level of output Q, for example, when A is low, when A is connected to ground? Let's say I take this wire and I connect it to low level, so 0. Maybe I'll even write it with this color. Do you have any guesses? You can write in the chat. If I connect A low, what level will be Q? Okay, somebody says 0. Let's look at this circuit in the following way. When I connect A to ground, then this gate of P-channel MOSFET is charged with negative carriers. So the channel attracts positive carriers, and P-channel conducts with positive carriers at the channel. So this transistor turns into, basically, it starts to conduct electricity. So electricity can go through this transistor and it becomes something like short circuit, right? So energy, current can flow through this transistor. On the other hand, this lower field effect transistor is also charged with negative carriers because A is connected to 0. So this is all with minuses, which attracts positive carriers. But for N-channel transistor to open, it needs N negative carriers at the channel, because this letter tells you what type of channel we need. So this thing stays shut because it doesn't have negative carriers at the gate. So as we can see, Q is connected through short circuit to 5 volts and disconnected with open circuit from 0 volts. So what will be the level of Q, high or low? Type in the chat as fast as you can. So somebody says high, that is correct. Okay, so that's the first step. And the second step is I'll use a different color, for example, red. So what happens if I take A and connect it to 5 volts, to high logic level? Can you write in the chat what will happen? What will be the value of Q? So when I connect A to high level, both gates are charged with positive charge, and they attract negative charge. So inside the channel, these pluses are repelled away and minuses are attracted. So negative carriers, electrons, are attracted to the channel in both field effect transistors. So, but for P channel transistor to conduct electricity, it needs positive charges. Here are negative. So in case A is high, P is shut. It doesn't conduct electricity. It's open circuit. However, N channel field effect transistor has electrons attracted to channel. Electrons are negative. So this thing starts to conduct electricity, becomes short circuit, starts to conduct the current. And so Q is disconnected from 5 volts and connected to 0 volts. So the value of Q will be how much? 0 or 1. Exactly, it will be 0. So this is how we can use field effect transistors to build logic circuits. And this is the output. So please tell me, how can we call this logic circuit given this truth table? So from programming, for example, so somebody says not a negation, not, okay, correct. So the truth table is A0 Q1, A1 Q0. It's called logic not. I will write the second meaning. We will call it also bitwise not. For 1-bit operations. Yeah, and that's all. So basically this is a not circuit. And also it has some schematic ways of drawing. So for example, in Latvia, we would have to draw this thing as a box, which is at least 10 millimeters wide and has inputs which are separated from the edge by 5 millimeters. If you, for example, wanted to draw a not element in your bachelor's thesis in Latvia, you would have to draw it this way, and you would have to write NE, which means which in Latvian just means not, inside this box, and here also 5 millimeters. But probably you don't have to know it, because you will most probably be using something like American way of writing. So not element in, for example, Logisim, which we will be using for our labs, is drawn this way. So this is also so the triangle basically means the repeater of the signal or a driver, and the ball at the end means the opposite, the inversion. So for other logical elements, if we draw an element and put a small ball at the end, it means invert the whatever was coming in. So this is the first logic circuit, and you you did pretty well determining the output. So we have 2 more circuits to analyze today. The next one will be this. So some people, I don't know why, pretty smart people, they decided to do the following, to bring the circuit to the next level, and they decided to connect 2 transistors in series in the top shoulder and 2 transistors in parallel in the bottom shoulder. And then they decided to connect the gates of one lower and one upper transistor and call it one input, and the other bottom transistor's gate with the other top transistor's gate and call it the other input. So we will call this A, and this we will be calling B, and this will be called Q. Oh yes, I forgot to tell you one more thing about this circuit. I'll write it with letters, but the first thing that we can check out is, and we can just remember that not gate. These are also called logic gates, not, you know, elements or something like that. They're called gates, and this is, you know, how we are going to call them. So not gate is built using how many transistors? 2 transistors, right? So we have 2 transistors. So whenever, you know, Intel or AMD tells their processors, their newest 11th generation Intel processor has, for example, 1 billion transistors, well, you know that at least 2 of these transistors were used to build a NOT element. And there are probably many NOT gates inside this processor, so you know how they're connected. And the second thing is, we need to talk about something called propagation delay. So propagation delay is basically time for signal to travel through gate, which is the same as saying time for MOSFETs to open or close, change state. Okay, so you know, when you set for example, from low to high, first of all, this charge has to, you know, the negative charge has to flow away and the positive charge has to flow in. That takes some time. You know, electricity travels with the speed of light, and in materials, the speed of light is even slower than in vacuum, for example. On the PCB, the speed of light is something like 2 times slower than in a vacuum. So, you know, this is the first thing that takes time. And the second thing is, even when the carriers are charged into the gate, we need some time for the charges inside of this bulk material to travel from more distant areas to the gate, to the channel, and to form the channel, and only then the current can start flowing. So it needs some time to happen. You would also agree that, for example, smaller transistors lead to faster switching, because everything is smaller, everything is more closely together. So you need to, you know, these carriers need to travel smaller distances for the thing to happen. So smaller transistors lead to faster switching. This is why, for example, you can have 4.8 gigahertz turbo boost on 7 nanometer technology, but you definitely cannot have it on, for example, 60 nanometer technology. So you make transistors smaller, the carriers need to travel less distance, so everything happens faster. And one more thing is that generally, regardless of the technology, the time for transistor to switch is relatively fixed for certain technology. For example, inside the CPU, all transistors are approximately equal in size, so all of them open and close approximately at the same time. So this time is called little Greek tau, and it's called propagation delay per one cascade. And the switching that happens in parallel happens at the same time, so it needs the same time to switch the gate, just one propagation delay, if the transistors are connected in parallel. If they are in series, then these times add up, but if they are in parallel, then the switching happens at the same time in all transistors, so the propagation delay is the same as if for one transistor. So my question to you would be, for example, how many taus do we need for NOT gate to change its output when we change the input? And I'll search for little tau. Tiny t letter. So for NOT gate to change its output when the input changes, it needs only one propagation delay or one tau, because both of these transistors receive the input at the same time, so they switch at the same time, so the output appears after just one propagation delay unit. So this tau is propagation delay unit measured in usually nanoseconds, for example. Well, let's look at an example. Let's say we have a processor which works at 4.8 gigahertz. So 4.8 gigahertz is 800 megahertz. And this is how many hertz. And the period is 20 or 200 nanoseconds. We, of course, want these gates to switch much faster than the maximum clock frequency. So let's say we want to give 10% of the total period of the CPU frequency for gate switching, and the rest of the time the signal should be stable. So we divide it by 10, and then I'll multiply it with milli, micro, nano. So we need these transistors to switch with a speed of at least 20 nanoseconds. You know, so both of them should switch in, for example, 20 nanoseconds. It's only possible if they're really, really small. Okay, so these are two things that we need to consider. First is how many transistors we need, and the second is how long time it takes for the gate to change the state. So let's analyze our next circuit, which is equally important, if not more. So this is connected like this: two transistors in series in top shoulder and two in parallel in the bottom shoulder. And one of each kind is connected with gates, and we have two inputs. So again, in the top part, we will have only P channel transistors. So their bulk is connected to the upper part, to the source is pointing up. So for example, 5 volts. here. And the bottom transistors are N type, and their bulk is connected to ground. So, and maybe even a little bit more correct way to draw it is because both of the upper transistors are located on the same wafer, the second transistor's bulk is actually connected to power supply directly. So 5 volts and 5 volts here. Because these transistors are located on the same piece of silicon, so their bulks are actually the same piece of material, so they're actually connected together. Something like this. So, but it's not really that important. It's just a technicality. So P transistors point to P channel, N transistors point from N channel to P wafer, like this. Okay, and now we have 2 inputs. Everything becomes 4 times more complicated because if you double the number of inputs, the combinations increase 2 times, so they're doubling, so it's exponential growth. So we have 2 inputs, A and B, and 1 output, Q. So how many combinations do we have? You're programmers, you should kind of tell me how many A and B combinations can we come up with? So A can be 0, B can be 1, A can be 1, and B can be 0. And, so you would agree with me that in total it will be 4 different combinations. And one way to systematically quickly fill this table is the first variable you change in every line. And the second one you change every 2 lines, 0, 0, 1, 1. And if we had third input, we would change it again 2 times slower, 0, 0, 0, 0, 1, 1, 1, 1. This way we will never make mistakes and have all combinations. So now we have 4 different inputs, input combinations, and we need to figure out what will be the output. So let's start with the simplest one. So B is connected to ground and A is also connected to the ground. Now we need to figure out how these transistors are going to be acting. So in the chat, you can try to figure out and type what will be the value of Q if A and B are both low. So somebody says that Q will be low. Do you have some other ideas? When A and B go down, which transistors start conducting and which ones stop conducting the current? So similar to this, when A was connected low, the upper transistor opened because its gate attracted the opposite of the channel. So P opens when input is low. So basically, I will even write it down so we can have a lookup. So P opens when input is low and closes when input is high, and opens when input is high. Okay, so A is low, so P channel will be conducting. actually open is a bad word because open circuit means that it doesn't conduct. So I'll write it a little bit differently. P becomes short circuit. So P becomes short circuit when input is low. And N becomes short circuit when input is. Okay, so with this helper text in this corner, so when input of a transistor, of p-type transistor is low, it becomes short circuit. So for this p-type transistor, input is low, short circuit. For the second p-type transistor, input is connected to be low, so it's short circuit. And N becomes short circuit when input is high. But since both inputs are low, both transistors are not conducting, they're open circuit. So Q is connected to 5 volts through both top transistors. So the value of Q when A is 0 and B is 0 is 1. Okay. Next case is when A is high and B is still low. What happens then? So first, let's deal with A's transistors. So when input for P channel is high, it doesn't conduct. So this one is closed. And when and for the N channel transistor, its input becomes high, so N becomes short circuit. So this transistor becomes short circuit. For B, nothing changed, right? So for B, this one would be short circuit and this one would be closed. So those two transistors didn't change. So what will be the value of Q? Will it be 1 or will it be 0? Quick, write in the chat. So Q with orange color has short circuit path to ground. And one of these two transistors is not conducting, so it is not connected to 5 volts. So the output is 0, correct. And as you can see in this way, because these top transistors are in series, we don't have some short circuit event when both the top and bottom transistors will be conducting and having short circuit and exploding or something like that. It's pretty stable. So the next combination that we will look at is this: A is low and B is high. What happens here? Can you tell me the answer right away? So A is low. P becomes short circuit when input is low. So A's P transistor will become short circuit. And when A is low, its N channel transistor becomes non-conducting, open circuit. For B, it's high, so its N channel transistor becomes short circuit, but its P transistor becomes open circuit, not conducting. So what will be the value of Q? Looking at the greens. So Q is not connected to 5 volts because of this green X, and it is connected to ground because B's N-channel transistor is short circuit. So the output will be 0. And the last final combination is with color pink. So 1 and 1. A is high and B is also high. So what will be the output? Can you immediately tell me? When A goes up, somebody says 1, okay. Think again. So when A goes up, its N-channel transistor opens and P transistor closes. So this doesn't conduct. And B, the same, it goes up. So its P-channel transistor doesn't conduct, but N-channel transistor conducts. So Q is connected to ground with both bottom transistors. So unfortunately, for those who thought it's going to be 1, it is still 0. I know it's hard for me when I studied this. It was really hard to kind of think through all these combinations, and there are so many transistors. And before studying this, I hadn't worked with any transistors, and now I have 4 transistors in my face. So I also didn't really understand it right away, but eventually, if you think about it, if you think about each individual transistor, you will figure it out. So this is the truth table of this circuit. And can you tell me what kind of an animal this circuit is? Programmers. Somebody says NOR gate and somebody says NAND gate. So which one is it? To help you understand it, we can just, with light gray color, write what is the opposite of Q. And the opposition is the line above the letter. So Q is Q, and Q with line above it is the inversion or the opposite. So actually for this NOT gate, we could also write Q is equal to A with a line above it. It's like A with inversion, inverted or the opposite. So Q inverted here will be 0, 1, 1, 1. So this would be OR, right? Either one or the other. Only if both inputs are 0, then the output is 0. Otherwise, it's like this. So this thing here, the actual Q is NOR. So those of you who said NOR, you're correct. Okay, next thing that we need to check out is what is the symbol of this NOR element. And in by Latvian standard, it's still a box. But in Logisim that we'll be using, NOR is drawn in the following way, like this. This is OR element, sorry. And it has a ball at the end, so it means the opposite. So this symbol would be OR, but with ball at the end, it is NOR, and it has 2 inputs, for example, like this. Next question for you, write in the chat as fast as possible. How many transistors do we need to build a NOR element with 2 inputs? This is not a trick question, so those of you who said 4 are correct. Next question, what is the propagation delay of this circuit? How many taus do we need to wait until changing the input propagates to the output? Somebody says 2 tau. Okay, but why? Let's say, because the inputs, they are changed at the same time. So let's say I change A low and B low at the same time. all 4 of the gates will receive the new level at the same time, and all of the transistors will start transitioning in parallel at the same time. They're not waiting for a previous transistor to change the state for the next one to change. This all happens simultaneously. So the propagation delay is actually just 1 tau. But I will give you an example where propagation delay will indeed be 2 taus, but not in this case. And finally, a trick question: can we build a NOR element with more than 2 inputs? What if I would want to build a NOR element with 3 inputs? Is it possible? The definition of NOR element is all input 0, output is 1, and in all other cases, output is 0. For example, for OR, you could have, for example, A or B or C. You could have multiple inputs, and the result would be whenever one of the inputs is 1, the output is 1, and only if all inputs are 0, the output is 0. So the same would apply for also NOR and also for transistor connections. So you can write in chat, can we build a NOR with multiple inputs, more than 2 inputs, and how could we do it? While I will be drawing something here. So A or is like a plus, B plus C, and so on, plus X equals Q is possible. And the truth table would be 0, 0, 0, 0, and so on. Zeros equal 1, 0, and 1, 0, 0, 0, and so on equals 1. So actually, the good thing about these NOR gates is you can add inputs simply by adding more transistors of P type in the top shoulder in series and more transistors in parallel in the bottom part, in the bottom shoulder. I'll try to, display it with an example. The free-form selection like this. I'll move this thing a little bit away. So let's say I want to add another input C. As I promised you, I just write C. I add one more transistor in series. Check, 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 like this. P type, no problemo. And one transistor in parallel. So let's check out the truth table. Only if all inputs are low, all series P-type top transistors are short circuit and Q is connected to power supply and is equal to 1. Even if I add more transistors in the top part, all inputs, even the added inputs, need to be low for the output to be high. And as soon as any input, be 2 or 3 or 5 inputs, any input goes high, it shuts the current from flowing to 5 volts and opens the gate for current to flow to ground, so the output is low whenever any of the inputs is high, right? So yes, I can add more inputs to this NOR gate without problem, right? So we can build NOR gate with 2, 3, 5, or 1 million inputs. It still is going to be, just as simple. Just add more transistors in top part in series and in bottom part in parallel. Okay? Understand there? Do you agree with me? Or do you disagree? Okay. Silence is acceptance. So I assume that you agree that I can add more inputs. But the trick question is, please type in the chat as fast as possible. What would be the formula to calculate number of transistors as a function of number of inputs? So let's say I have 3 inputs. How many transistors do I need? Let's say I have 100 inputs. How many transistors do I need to build a NOR gate for that amount of inputs? Two times the number of inputs. In general, transistor count n equals to 2 times the amount of inputs. Exactly. Each input adds 2 transistors. And actually, if you think about it, what happens if I have only one input? So what happens if I have just one input? It kind of becomes this NOT gate, don't you agree? Yeah, somebody already wrote it. So if we lower it down to one input, it becomes NOT gate, which is kind of true. And the next question is, what is the value of propagation delay as a function of number of inputs? So I have two inputs. We had propagation delay 1. What happens if I have 3 inputs or 4 inputs or 100 inputs? What is the value of propagation delay? So propagation delay is it's still 1. Those who say it's still 1, they're correct. So propagation delay is still 1 tau, regardless of number of inputs. Well, of course, theoretically, if we have 1 billion inputs, we need kind of a lot of energy to switch them all at the same time and so on. But that's not kind of our problem anymore, because we don't have such cases. In cases where the number of inputs is low, it's just 1 tau, it's the same, because all the inputs receive information at the same time in parallel. So all transistors transition in parallel, so it's just 1 tau. Wonderful, you are very smart people. So now I can go to our final circuit, which is the following. So somebody said, this is fine, but let's do it the opposite way. I'm going to connect top p-channel transistors in parallel and the bottom transistors in series. And let's see what happens. Maybe it was initially just a joke, but let's see what it turns into. So we have power supply, and then we have transistors in parallel, P channel transistors, P channel like this. Oops. So, and this will be the output. So it's connected in parallel. And the bottom transistors this time are connected in series. And again, these bottom transistors, they have the same, they're put on the same material, so their bulks are kind of connected together and to ground. So these are N channel. So from P bulk to N channel. Oh no. Did I draw it wrong? From P, oopsie. This one was correct. Oh no. So I drew these transistors in the wrong way. I need to fix it so you cannot sue me and ask for your money back from the university. So P channel and bulk like this. And N channel like this. And here also yeah, I fixed it. Well, you are not telling me thank you for all the things that I said correctly today, but you noticed this one mistake and you immediately attack me. Okay, just kidding. So in this case, top P channel transistors are connected in parallel and N channel transistors connected in series. So I'm going to again connect these two gates together. This will be input A, and the other two gates. Okay, maybe this is not the best way. Somebody says this time it's NAND. Well, you have graduated my course. Congratulations. So be. Does everyone agree that this is a NAND gate? Let's check it out real quick. So we have inputs A and B and output Q. Combinations are A, 0, 1, 0, 1, B, sorry, 0, 0, 1, 1. So I set both inputs low, both inputs go down. In this case, both P channel transistors will be short circuit and both N transistors will be not conducting. Okay, maybe I'll just delete this. Use the colors right away. So 0, 0, the output is Q is connected through both top transistors to 1. Next, it was the color orange. So A we set high and B stays low. So when A is set high, its P channel transistor stops conducting and its N channel transistor starts conducting, but the other two transistors didn't change their states because B stayed 0. So Q is still connected to 5 volts through B's P channel transistor and disconnected from ground through B's N channel transistor. So the output is high. Next, green color. Let's say we swap them. So A goes down and B goes up. So A's p-channel transistor starts conducting in the top part and stops conducting in the bottom part. And B's transistor stops conducting on top part and starts conducting in the bottom part. But it doesn't matter because A's one is short and A's top transistor is connected high. So in case A is 0 and B is 1, the output is still 1. And finally, when both inputs are high, then both p-channel transistors are short, do not conduct electricity, and both n-channel transistors are open, short circuit, and connect the Q to ground, and only if both inputs are high, the output is finally low. So what is the name of this gate? I'll write in bright gray the opposite of Q. The opposite of Q would have been 0, 0, 0, 1, and this would be called NAND, but we have this opposite of AND, so this is called NAND. So somebody kind of spoiled all of the surprise by shouting out right away that this is NAND gate. Correct. So let's see, this is NAND gate. How do we draw it? We draw it in the following way. In Logisim, it's like this. It's like, letter D with a ball at the end. So this is a bit crippled like this. So this is NAND gate because this kind of big D is AND and the ball at the end says inverted. So it's the opposite of AND, it's NAND. Okay, finally, quickly, how many transistors and how many propagation delays for this thing to change its state? So number of transistors for propagation delay is 1 tau. Correct. And in general, again, you would agree that I can add an infinite amount of parallel transistors in the top part and infinite amount of series transistors in the bottom part, and still only when all of the inputs are high, this bottom chain would start conducting and Q would be low. In all other cases, the Q will always be high because there will be one input high, one input low connecting Q to low to high and cutting Q from going low. So in general, number of transistors, actually I can copy it from here. So we can add more transistors and more inputs. And the same rule applies. So number of transistors is 2 times the number of inputs, and propagation delay is still 1 tau. Doesn't matter how many inputs we add. Okay, so this is about not NAND and NOR gates. And now let's look at the next thing. So I see that some of you kind of got this thing very well. Now let's, I'm going to ask you, well, how can I build other logic circuits? For example, how can I build AND gate? can you come up with an AND gate using transistors? You know, connecting them somehow so that we get a AND gate. You can write it in the chat or you can answer with your voice. And if you know how to build an AND gate from transistors, you can also share your screen and show it to everyone. Okay, so the truth is that building an AND gate, people have tried to do it, but it has never become easier, at least not with these depletion mode field effect transistors, than to just take an NAND gate and put NOT gate at the end of it. You know, people have tried playing with these transistors, you know, changing them in places and turning them upside down, but unfortunately, nothing simpler than NAND than NOT hasn't really been developed. So, well, at least not officially. We don't know what happens inside these Intel and AMD labs, but generally, AND gate you can easily build by taking NAND gate and putting NOT gate at the end, right? Like this. So, you know, I could copy these schematics, but you can maybe answer right away. How many transistors do we need to build an AND gate? And what will be the propagation delay? Okay, so somebody says 6 transistors and 2 tau. Exactly. So basically, this is the reason, because AND gate needs more transistors and is 2 times slower. Imagine 2 times slower. Most logic circuits, if not all, are always kind of being made using only NOT, NAND, and NOR. Not instead of using only AND and OR gates, which are easier for human to process. Because these NAND and NOT gates, well, they're not so easy to get around with. What is NOR? I can't tell you really. So only if all inputs are low, the output is high. In all other cases, it's low. And the NAND gate is also kind of hard to grasp. So using AND and OR gates would be easier for a human mind, but in reality, it would be slower. So can't we build AND gate with just 2 transistors? Probably not. At least not in this CMOS technology. For some reason, for some reason, depletion type transistors are not really used for this. So in reality, no. So the same goes for OR gate. I'll just type it here. So OR gate, in all practicality, is being built taking NOR gate and putting NOT at the end. And you will agree with me that it's the same story. It's still 6 transistors and 2 taus. So Actually, in Ortus, I don't know if I have put it there, but Ortus, I think you have a homework where you need to come up with a transistor connection that creates XOR. Let's see, do you have a homework here? Only labs. Okay, I'll translate this homework and put it in Ortus. But generally, you have a homework where you need to come up with XOR circuit. And I think probably XOR and also XNOR. So it's kind of XOR is, exclusive OR, and XNOR is kind of exclusive NOR, or the opposite of XOR. And these ones are actually possible to build using transistors, but you can also try to build them using just NAND, NOT, and NOR gates and see which way uses less transistors, okay, and has a smaller propagation delay. You can try to find XOR and XNOR circuits on the internet, but be aware that some of them have mistakes. So you kind of have to really go through all cases of inputs, figure out the state of each transistor, and only then you can kind of submit your final answer. This is one way. The other way is you can also try to build XOR and XNOR using NAND, NOR, and NOT gates. Maybe it will be even easier. Something like taking two NAND gate, two NOR gates, for example. They already have one here, and if you invert everything, you'll have it in the opposite way. So on, maybe you can manufacture them there, but you have to do this homework as soon as I put it in Ortus. So do you have some questions about these transistor gates? I'll just type it like this, homework. There. I think that it's actually all for these transistor circuits. And the next topic that we have is binary numbers. Okay. So please type in the chat how many of you feel comfortable about binary numbers, the ones that consist of ones and zeros. Can you add them together? Can you, multiply them maybe, and so on? I guess many of you are actually programmers, so you feel good about binary numbers. It's not something that you are kind of scared of and so on. So I will also put in Ortus a very simple homework where you just need to do some basic things with binary numbers so that you really revise it, at home at your own pace. But we will take a small, look at the binary numbers, about how we can add and subtract them and how we can multiply them. So a small recap, let's say we have two binary numbers, with black. So 1 0 1 1 1 0 0. Oh, this is a boring number. Let's use something better. So here will be 0, here will be 1, here will be 0, and here will be again 0. Okay, so how do we add them? We add them just one by one. Let's say we want to add them. 1 plus 0 is 1. 1 plus 1 is how much? It's 10. 0 here and 1 in top. 1, 0, 0 is 1, and 1, 0 is 1 again. So something that we need to remember is if we add two n-bit numbers, how big will be the result? How many bits will be the result? So let's say you add two 8-bit numbers, how big can become the result? What's the maximum size of the result? I'll give you some example. Worst case scenario. Let's see, we want to add 1, 0, 0, 0 and 1, 0, 0, 0, two 4-bit numbers. Actually, first computers were built as 4-bit computers because, well, that was the maximum number of bits that the technology at that time could manage. So first CPUs were actually 4-bit CPUs. So 0 plus 0 is 0, 0, 0, 1 plus 1 is 10. So we can get at most, for example, 5 bits of 4-bit addition. So n bits plus n bits is n plus 1 bits. That's true. And if we multiply two numbers, how do we multiply two binary numbers? Well, we multiply them the same way as we multiply decimal numbers. So we take one number and multiply all the top number with it. It's just so much easier because here is just we multiply with 1. So it's basically the same number, 1, 0, 0, 1. Next, we add 1, 3, 0 at the bottom, and then we multiply with the next number. Since it's 0, all of this results in zeros, so it's really simple. Next is 1. If it's 1, then we just rewrite the top number. And again, 1, we rewrite the top number. And then we just add everything together. So the question remains, if we multiply two n-bit numbers, what's the maximum size of the result? So it's 2n exactly. It's just some things that we need to kind of remember. So generally, I will leave you to do the homework at your own pace. And I'll not really bore you with some basic binary things because many of you already know it. And those of you who don't know it, you can just revise it. So I'll put the homeworks in Artus. You have to do them for the next lecture that we have. And I will probably also translate the test. So you will have a small test about the logic circuits of the transistors and field effect transistor way of working, something like that. And you can do those. And for the next lesson, please revise the binary number operations. And next time, we will have a very interesting and intensive lesson because we will teach these logic gates to do the arithmetics for us. For example, I added two numbers together. It was boring. Can I teach logic gates? Can I teach transistors to do arithmetic and arithmetic operations? But that we will do in the next lesson. So that's all for today. I will put the homework and the test. Please do it for the next lesson. And then we'll do some very interesting stuff next time. So that's all for today's lesson. You can ask some questions if you have them.